So last time we have studied the properties of greatest common divisor. Now we shall consider some problems. So these are the problems set 2.1. It is problems 2.2 from the book. Consider the first problem for integer n greater than or equal to 1. Use mathematical induction. To prove that 21 divides 4 to the power n plus 1 plus 5 to the power 2n minus 1. So this is what we have to prove for integer, or you may say for any integer. For any integer n greater than or equal to 1, 21 divides 4 to the power n plus 1 plus 5 to the power 2n minus 1. Now you consider any integer n greater than or equal to 1, the smallest will be 1, and then this result can be verified, or n is equal to 2, etc. We shall use the method of mathematical induction to prove this result. Now, solution. We know what is the method of mathematical induction. There are two steps. Prove this result for n is equal to 1, and prove the second step or second case is assume the result is true for n is equal to m, and then prove the result is true for n is equal to m plus 1. Then that result will be true for all values of n, positive integers. Now consider this result as we have to prove 21 divides 4 to the power n plus 1 plus 5 to the power 2n minus 1. Now we use mathematical induction. We use the method of and in this the first step is prove the result. Suppose this as a result or statement 1, prove this result is true for n is equal to 1. Case 1, or we can say is case 1, and the result to be proved for n is equal to 1. Case first, for n is equal to 1. Now when n is equal to 1, we have this. If n is equal to 1, 4 raised to n plus 1 plus 5 raised to 2n minus 1 is equal to 4 to the power, n is 1 means 1 plus 1 plus 5 raised to 2 into 1 minus 1, or this is 4 square plus 5 raised to 1, that is 5, or which is again 21. Now obviously 21 divides 21. So since 21 divides 21, this 21 divides, the value of this is 4 raised to n plus 1 plus 5 raised to 2n minus 1 if n is equal to 1, and therefore 1 is true for n is equal to 1. Therefore 1 is true for n is equal to 1. So we have verified the result, it becomes true for n is equal to 1. Now the second case of second step of mathematical induction. Step 2. Assume 1 is true for n is equal to m. Assume that 1 is true for n is equal to m. And what this shows, the result, replace n by m, that is 21 divides 4 raised to m plus 1 plus 5 raised to 2m minus 1. So this is true. We may refer this as second result. Now we have to prove that the result is true, prove that 1 is true for n is equal to m plus 1. And that is to prove. Now see what the result will be for this case. N is equal to m plus 1. Replace n by m plus 1. So 21 divides 4 to the power m plus 1 plus 1 plus 5 to the power 2 m plus 1 minus 1. So this we have to prove. Now consider the this number. Now 4 to the power m plus 1 plus 1 plus 5 to the power 2 into m plus 1 minus 1. This can be written as. Now we have to use this result. That means we know 21 divides, or we assume 21 divides 4 raised to m plus 1. So we shall consider this expression or this combination separate from this expression. So this can be written as 4 raised to 1 can be separated. We write 4 into 4 raised to m plus 1 from this using the laws of indices. And similarly here we want 5 raised to 2m minus 1. See here 2m plus 2 minus 1, or we can consider 2m minus 1 and then plus 2 can be separated, and that is plus. So 5 square we shall write separate 5 square and then 5 raised to 2m minus 1. You can verify this. Power remains same, value is not changed. And next, this is equal to, from this we shall consider the coefficient of this term, which is 4, common, and in bracket we write the expression this first, 4 to the power m plus 1 plus 5 to the power 2m minus 1, because we want this combination. But again the value is to be the same, so we should add and subtract the additional extra terms that we have considered. And you see 4 into 4 raised to m plus 1, that is the same. But this term is not there. 4 into 5 raised to 2m plus 1 is not there. So we subtract that term. That is minus 4 into 5 raised to 2m minus 1. But this term should be there. So we add that term. Plus 5 into 5 square into 5 raised to 2m minus 1. So this is the adjustment of terms without changing the value, and you should note this. How we have written. We have added this term, we have subtracted, and the original term is written last. And further, this is equal to, I shall write here, this is equal to 4 into bracket 4 raised to m plus 1 plus 5 raised to 2m minus 1. And you see, from this 5 raised to 2m minus 1 is common. And if this term is taken common, what remains in bracket is minus 4 plus 5 square. And minus 4 plus 5 square is minus 21. It is plus 21. 5 square minus 4 is 21. So this is 21 into 5 raised to 2m minus 1. And now this is the expression, right side. So we have 21 divides this number and 21 divides 21. So therefore this expression is a combination of these two, this bracket and this bracket. And if A divides B, A divides C, then A divides combination of B and C. So therefore 21 must divide this expression, that we can write. So we have 21 divides by second. So we have 21 divides, say 4 raised to m plus 1 plus 5 to the power 2m minus 1. This is by 2. And 21 divides 21. This is obvious. Every number, every integer divides itself. And thus 21 divides combination of these two, and combination of these two is here. So therefore 21 divides, and multiply this by 4, this number by 4, multiply this by another number 5 to the power 2m minus 1. So 21 divides 4 into bracket 4 raised to m plus 1 plus pi to the power 2m minus 1 plus, or we may write 5 raised to 2m minus 1 first and then 20. That is, this is, but you see, this is same as this one, and thus 21 divides this number means the left side number, and therefore 21 divides 4 to the power m plus 1 plus 1 plus 5 to the power 2m plus 1 minus 1. From this expression it is the same, and thus this proves that the result 1 is true for n is equal to m plus 1. We can replace here n as m plus 1. You see the result remains the same. So this shows that 1 is true for n is equal to m plus 1, and thus we have proved the second case also in the induction, and or second step in the induction, and therefore by 1 and 2 and by mathematical induction the result 1 is true for all positive integers n is equal to 1, 2, 3, etc., and therefore by 1 and 2 1, the statement 1 is true. 1 is true for n is equal to 1, 2, 3, etc. all values. That is, 1 means this result is true, and n is equal to 1, 2, 3 means n greater than or equal to 1, or n greater than or equal to 1, and this completes the solution. So we have used the method of induction. Now we shall consider a second example. So we here use the theorem 2 here by theorem 2. Result: A divides B, A divides C, A divides Bx plus C1. That result is used. And now we shall consider for any integer A, if A is odd, then A square divides. Then further, second example we will have, and that is I shall write here, for any arbitrary integer A, if A is odd, then prove that (32) divides 32 divides A square plus 3 into A square plus 7. So this is the result that we have to prove. Now we shall consider the solution. A is odd. Any integer by the division algorithm can be written in different forms. Now if you divide by 4, then it will be, what are the possibilities for the remainder? If you divide by 4, the remainder will be either 0 if it is divisible by 4, or the remainder will be 1, or the remainder will be 2, or maximum the remainder will be 3. And therefore any integer on division by 4 can be written in the form see one of the form, that is in the form 4q or 4q plus 1. If the remainder is 0, then it is 4q, or if the remainder is 1, then it is 4q plus 1, or if the remainder is 2, then it is 4q plus 2, or if the remainder is 3, then it is 4q plus 3. So this is the case. You can verify this. Consider any integer, say 78, etc. And if you divide it by 4, then what is 1? It will be 1 of the type. So what is the quotient? Say, and then the next is 9. Quotient, next 9 quotient is 9. So then this is 36, and therefore what is the remainder is 2. So therefore it is 4 into 78 is 4 into 19, or 19 into 4 plus 2. Here or then this is of the form 4q plus 2. Remainder is 2. So it will be one of the 4 forms. And among these, now in the problem it is given that if A is odd, now you see out of these 4 which are odd and which are even. First 4q, this is not odd because it is multiple of 4 means multiple of 2. So this is not odd, and again this is not odd, this is even because 2 is common for this. So only odd are 4q plus 1 and 4q plus 3. These two are odd. So we have to consider A is 4q plus 1 or 4q plus 3. Now consider if A is odd, then A is equal to 4q plus 1 or A is equal to 4q plus 3. One of these. Now we have to consider these two separately. Now suppose first let A is equal to 4q plus 1. First let A is equal to 4q plus 1. And what we have to show is A square plus 3 into A square plus 7 is multiple of 30. We have to form this product. So first or we write this as A square plus 3. Therefore A square plus 3 into A square plus 7. This is equal to, that will be 4q plus 1 whole square plus 3 into 4q plus 1 whole square plus 7. Now this part of arithmetic you simplify this. What is the square of 4q plus 1? 16q square. Plus then the middle term will be 8q, you check, and plus 1 plus 3, that is plus 4, and here also 16q square plus 8q plus, and this is 1 plus 7, 1 plus 7 is 8, this integer. And now you may see from the first bracket what is common, it is 4 can be taken common, and from the second bracket 8 can be taken common. So that means common term is 32 into bracket. Here the 4 is taken common, and in bracket 4q square plus 2q plus 1. And here what remains in another bracket is from this 8 is taken common, 2q square plus q plus 1. And thus we have 32 is a divisor of this expression. So this is multiple of 32, and 32 divides this expression. Or this may be considered as 32 is equal to, suppose this number is m and this number is n. And therefore 32 divides, so this shows that 32 divides a square plus 3 into a square plus 7. this is the first case. If A is equal to 4q plus 1. Now similarly the second case can be considered. Next let, and in the same way we can consider, we can prove this. Let A is equal to 4q plus 3, and I think you can do this yourself and show likewise. Is here 4, instead of 4q plus 1, consider A as 4q plus 3, and you take some terms common which are possible, and then show 32 is multiple of this number, and thus 32 divides. The next part we shall study is the Euclidean algorithm. So Euclidean algorithm is a process to obtain greatest common divisor of integers which are large. So for smaller integer we can obtain it easily, but for bigger integers, so we have to use this method, which is Euclidean algorithm. First we shall state a lemma, state and prove a lemma. If A is equal to QB plus R by division algorithm, A is divided by B, Q is quotient, R is remainder, then GCD of AB is equal to GCD of BR. So this we shall prove. If this is the equation where we can write, then GCD of these two integers A and B is same as GCD of B and R. Now the proof. So given A is equal to QB plus R, then we should consider now the GCD of AB is equal to D. Let GCD of AB is equal to D. So this implies D divides A and D divides B. So this will imply D divides combination of A and B, and the combination of A and B we shall consider as A minus QB. D divides A minus QB, and this will imply D divides, what is A minus QB? A minus QB is R, and thus now we shall consider, since this is A minus QB is R. So thus we have D divides D and D divides R. And this shows that D is a common divisor of D and R. That is, but we want to show D is greatest common divisor of B and R. These are equal, means this we assumed as D. So the second property we shall consider, if C is any other common divisor of B and R. Or any common divisor of B and R. That is, C divides B and C divides R. Now if C divides B and C divides R, C divides combination of it. So therefore, then you can say C divides combination of B and R, we shall consider as QB plus R. Theorem 2. Here also we are earlier used theorem 2 result here, and thus C divides QB plus R means C divides A. And so what this shows that C is common divisor of A, and C is also common divisor of B. We have here. So C divides A and C divides B. So therefore we have C divides A and C divides B. that is C is common divisor of A and B, but what is the greatest common divisor of A and B? It is D. But GCD of A and B is equal to D, and therefore this C must be less than or equal to D. So therefore C is less than or equal to D by definition of greatest common divisor. And again you see D is common divisor, and if D is any other common divisor of B and R, then C is less than or equal to D. So therefore this also shows that D is the greatest common divisor of B and R. So by definition of GCD, GCD of B comma R, we have GCD of B and R is equal to D, and thus this shows that the two GCD are equal. GCD of A and B is D, and GCD of B and R is also D, and thus GCD of AB is equal to GCD of BR, and this proves the result. So, okay, thank you.